Hello, in this lecture we'll answer two questions. In the first question, we'll find out the area of this big circle, and in the second question, we'll find out the area of this rectangle ABCD in two different ways. So, start with the first question. In the drawing, we have those two circles that touch each other at this point C. Point C is the point of tendency of those two tangents, of those two circles with each other. In addition, we know that this is line segment CB, that is equal to 9 units in its length. This is line segment AC, that is equal to 16 units in its length. And we also have here tangent DE, that is tangent to this small circle at this point B. In addition, tangent DE is tangent to this big circle at this point. So we define the point of tendency of the big circle with this tangent DE. This point is point M. This is point B, that in relation to this big circle, it is an external point. From this common external point B, we have tangent VM that is tangent to this big circle at point M. In addition, from the same common external point B, if we draw this straight line and extend it, it will cut the big circle at this point C and A. So here we can implement rule 10. We'll repeat quickly on rule 10. Rule 10 is true in any circle. So in any circle, if AB is any chord, here AB is a chord in this circle, and PT is a tangent. PT is a tangent to this circle at point T. So from the common subpoint point P, we have tangent PT, and we also chord AB. So in this domain, the following equation will be true: that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can implement rule 10 in our drawing. Because in our drawing, for this common subpoint point B, we have tangent BM. Tangent BM is tangent to this big circle at point M. In addition, from the same common subpoint B, if we draw this straight line, it will cut the circle at 2 points. This is point C and point A. So we have here also chord AC. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation will be true: that BM square equals to BC times BA. Again, BM square equals to BC times BA. So I write it down. So BM square equals to BC times BA according to rule 10. I'll repeat again. If we focus on the common start point B, according to rule 10, the following equation is true: that BM square equals to BO times BA. Again, BM square equals to BO times BA. Again, BM square equals to BC. BM square equals to BC times BA. Again, according to rule 10, BM square equals to BC times BA. BM is the missing tangent, so we know what it is. So we have BM square that is equal to BC. BC is 9 times BA. BA in total is 9 plus 16, that is 25. So BA is 25. So in total, we have to find out that according to rule 10, BM square equals to 9 times 25. Here we take a root out of this equation and we get that BM, the length of tangent BM, is equal to the square root of 9, that is 3, times the square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. BM equals to 15 units in its length. The length of this standard BM is 15 units. In the next step, we will do a construction. That is to say, we will draw a common tangent to both circles at point C. Okay, again, we draw a common tangent at point C to both circles, to the small circle and to the big circle. And we'll define the touching point of the common tangent with tangent DE. This point is point N. Tangent, the common tangent CN is tangent to this small circle at point C, and the common tangent CN is also tangent to this big circle at the same point, point C. Okay. In the next step, we will join point C and M together by a straight line. And we will focus on this common external point, point N. From this common external point, point N, we have two tangents to this small circle, tangent NC and tangent NB. And according to rule 2, they are equal to each other. That is to say, the length of tangent NC is equal to the length of tangent NB. So I will repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle, and this is the common external point, point P. For this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, the length of this tangent PA is equal to the length of this tangent PB. P equals to PB. So we can implement rule 2 in our drawing. Why? Because, as I mentioned before, from the common external point, point N, we have two tangents to the small circle, tangent NB and tangent NC. And according to rule 2, they are equal to each other. This is to say, NB equals to NC. So in the next step, we'll copy this triangle C and B in a new page, and we'll analyze this triangle C and B. So actually, this is triangle CNB, this is the copy from the original drawing. According to rule 2, side CN equals to side NB. And we have the rule that says that in front of equal sides in the triangle there are equal angles. Repeat again, in front of equal sides in the triangle there are equal angles. So in front of this side CN, we have this angle, that is actually angle CBN. In front of this side NB, we have this angle, that is angle NCB. And because of the fact that those two angles are located between those two equal sides, they must be also equal to each other. That is to say, they have also the two angles have the same size. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. So in conclusion, we found out that angle NCB equals to alpha. This is angle NCB that is equal to alpha. And also angle CBN is equal to alpha. We will continue to focus on this common standpoint point N. From this common standpoint point N, we have two tangents to this big circle. We have tangent NC and tangent NM, and according to rule 2, they are equal to each other. That is to say, NC equals to NM. So in the next step, I'll copy the right triangle C and M in a new page, and we will analyze this triangle C and M. So actually, this is triangle CNM that I copied from the original drawing. In this triangle CNN, in this triangle CNM, side CN equals to side NM according to rule 2. And according to the same rule that I mentioned, the rule states that in front of equal sides in the triangle there are equal angles. In front of this side CN, we have this angle that is angle CMN, and in front of this side NM we have this angle that is angle NCM. And because of the fact that those two angles are located between those two, in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. So in conclusion, we found out that angle MCN equals to beta. This is angle MCN that is equal to beta. And angle CMN also equals to beta. In the next step, I'll copy the big triangle MCB in a new page and we analyze this big triangle MCB. So actually, this is triangle CMB that I covered from the original drawing. We know that the sum of the angles in any triangle is equal to 180 degrees. And therefore, the sum of the angles in this triangle CMB must be equal to 180 degrees. So which angles we have in this triangle CMB? We have this angle that is alpha, plus this angle that is beta, plus the big angle that is beta plus alpha. In total, the sum of those three angles must be equal to 180 degrees according to the rule that I mentioned. So in this of the equation we have alpha plus alpha is 2 alpha, beta plus beta is 2 beta, so we have 2 alpha plus 2 beta equals to 180 degrees. Here we divide this equation by 2, and finally we get that alpha plus beta equals to 180 degrees minus 2 is 90 degrees. So we can find out that the big angle MCB that is equal to beta plus alpha is equal to 90 degrees. It is a right angle. So this is the big angle MCB that is a right angle. It is given us in the question that AB is the straight line. Okay, AB is the straight line according to what is given us in the question. So if we focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line AB at point C? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, angle ACM is a peripheral angle that's located inside this big circle. In the next step, we'll join points A and M together by a straight line. By joining points A and M, we can deduce chord AM. Chord AM is a chord inside this big circle. So we have here peripheral angle ACM. This is peripheral angle ACM, and according to rule 3, peripheral angle ACM is a right angle. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must be subtended on the diameter of the circle. So repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So, in the drawing, we have peripheral angle MAN. This is peripheral angle AM. This is peripheral angle MAN. And peripheral angle MAN equals to 90 degrees in its size. And because of the fact that peripheral angle MAN equals to 90 degrees in its size, it must be located on the diameter. It must subtend on the diameter of the circle. Peripheral angle MAN subtend on MN, and therefore MN must be the diameter of the circle according to rule 5. So any peripheral angle that is a right angle must subtend on the diameter of the circle. We can definitely implement rule 5 in our drawing. Why? Because in our drawing, this is peripheral angle MCA, and peripheral angle MCA is equal to 90 degrees in its size. So according to rule 5, peripheral angle MCA that is a right angle must subtend on the diameter of the circle. Peripheral angle MCA subtend on AM, and therefore AM must be the diameter of the big circle according to rule 5. This big circle according to rule 5. So I write it down. So according to rule 5, chord AM is the diameter of the big circle. We also know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. And therefore, the center of this big circle must be located on chord AM, that is the diameter of this big circle. So, this is the center of the big circle. We define the center of the big circle. This point is point O. You can see here that this is point O, that is the center of this big circle, and point O is definitely located on AM, on chord AM, that is the diameter of the big circle, this big circle. So point O is the center of this big circle, point M is the point on the circle itself, so OM is the radius of this big circle. We define the radius of this big circle as R, so OM equals to R. And because of the fact that the radius OM of this big circle is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever you have radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in the next step, I'll copy the right big triangle, triangle A and B in a new page, and we will implement the Pythagoras theorem on this right big triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AB, and the length of the hypotenuse AB is 16 plus 9, that is 25. This is side MB, that is equal to 15 units in itself according to rule 10. Side AM is the missing side, so we find out the value of the missing side AM according to implementing the Pythagoras theorem in this right big triangle A and B. Here by PT is abbreviation for Pythagoras theorem. So actually, this is triangle A and B that are covered from the original drawing. According to the Pythagoras theorem, in this triangle A and B, AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. Again, AB squared equals to AM squared plus MB squared. So I write it down. AB squared, that is the square of the hypotenuse, is equal to AM squared plus MB squared. The hypotenuse AB is 25, therefore AB squared is 25 squared, that is 625, and it is equal to AM squared. AM is the missing side, so we leave it as it is. So it is AM squared plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total we found out that 625 equals to AM squared plus 225. Here we subtract 225 from this equation, and we get that 625 minus 225 is 400, so 400 equals to AM squared. Here we take a root out of this equation, and we get that AM is equal to the square root of 400, that is 20. So the length of this side AM is 20. And we already found out that chord AM is the diameter of the big circle. So here, AM is the diameter of this big circle. We know that the radius of any circle is half of the diameter. So if the diameter is 20, the radius must be equal to 20 over 2, that is 10. So the radius of the big circle is the diameter AM over 2. AM is 20, so it is 20 over 2, that is 10. So we shall find out that the radius of the big circle is equal to 10 units in its length. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Okay, again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of the big circle must be equal to pi times the radius of the big circle squared. The radius of the big circle is 10, therefore the radius squared is 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. 100 pi is 314.159 square units. So if we found out that the area that we are looking for in this question, that is the area of this big circle, equals to either 100 pi square units, so in terms of numbers, the area of this big circle equals to 314.159 square units. We finish with the first question. In the next step, I will present to you the second question, and we'll solve the second question in two different methods. Our our mission in this second question is to find out the area of this rectangle ABCD. So in the drawing we have rectangle ABCD and we have also this semicircle. We know that this is 9/7 MA, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So we start with the first method. Because of the fact that ABCD is a rectangle, all those 4 angles inside rectangle ABCD are right angles. So actually, this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. We define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle. So A equals to x units in its length according to our definition. In the next step, we'll define the point of tendency of this tangent DC with this semicircle. This point is point E. And we'll join points O and D together by a straight line. So what is the definition of line segment OE? Line segment OE starts from point O, that is the center of the semicircle, and ends at point E, that is a point on the semicircle itself. So this is exactly the definition of a radius. Therefore, OE is the radius of this semicircle, and the radius of this semicircle is equal to x units in its length according to our definition. So OE equals to x. Because of the fact that the radius OE that is equal to x, the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. By doing this construction, we can do quadrilateral EDAO. Inside this quadrilateral EDAO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral AOED we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral DEOA as a rectangle because it has 4 right angles. So this quadrilateral DEOA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side EO must be equal to the opposite side DE. Side EO must be equal to the opposite side DA. But EO equals to x, therefore DA must be also, the opposite side DA must be also equal to x units in its length. In the next step, we define the length of this line segment OB as A. And we define the length of this line segment MB as B. and we join points O and M together by straight line. What is the definition of line segment OM? Line segment OM starts from point O, that is the center of the semicircle, and ends at point M, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OM is the radius of this semicircle. It is equal to x units in its length according to our definition. In the next step, I'll copy the right triangle OMB in a new page, and we'll implement the Pythagoras theorem on this right triangle, triangle OMB. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle OMB that they call it from the original drawing. According to the Pythagoras theorem, in this right triangle OMB, OM square, or MO square, that is the square of the hypotenuse, equals to MB square plus BO square. So I write it down. MO square, that is the square of the hypotenuse of the right triangle MOB, is equal to MB square plus OB square. The hypotenuse MO is x, therefore MO square is x square, and it is equal to MB square. MB is B, therefore MB square is B square, plus OB square. OB is A, therefore OB square is A square. So in total, according to equation 1, we actually found out that x square equals to B square plus A square. In the next step, I'll copy the right big triangle A and B in the new page, and we'll implement the Pythagoras theorem on this right triangle A and B. The hypotenuse AM equals to 5 units in its length according to what is given us in the question. Side AB equals to B according to our definition. And side AB in total equals to x plus A units in its length. Here by PT is the evaluation for Pythagoras theorem. So actually, this is the right triangle A and B, the right big triangle A and B that are coming from the original drawing. According to the Pythagoras theorem, in this triangle A and B, MA square equals to MB square plus BA square. Again, MA square, that is the square of the hypotenuse, equals to MB square plus BA square. So I'll write it down. MA square, that is the square of the hypotenuse, equals to MB square plus AB square. The hypotenuse MA is 5, therefore MA square is 5 square, that is 25. This is equation 2. So 25 equals to MB square. MB is B, therefore MB square is B square plus AB square. AB is x plus A, therefore AB square is x plus A square. So in total, according to equation 2, we should find out that 25 equals to B square plus x plus A square. So 25 equals to B square plus A plus x plus A square. X plus A square equals to x square plus A square plus 2 times x times A. So in the right side of this equation 2, we have the expression of B square plus A square. And according to equation 1, we have already found out that B square plus A square equals to x square. Therefore, we substitute B square plus A square in this equation 2 by x square from equation 1. And we do it now, and we get that according to equation 2, 25 equals to B square plus A square is x square according to equation 1. So we have x square again plus 2xa. So according to equation 2, we actually found out that 25 equals to x square plus x square plus 2xa. So 25 equals to x square plus x square is 2x square plus 2xa. Here we divide this equation 2 by 2, and we get that according to equation 2, 25 over 2 is 12.5, and it is equal to 2x square over 2 is x square, plus 2xa over 2 is xa. So in total we found out that 12.5 equals to x square plus xa. So 12.5 equals to x square plus xa. So we take out x as a common factor from those two expressions. So x is taken out as a common factor. So what is left from x square after we took from it x as a common factor? What is left is x. What is left from xa after we took from it x as a common factor? What is left is actually a. So in total, according to equation 2, we actually found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of rectangle ABCD times the width of rectangle ABCD. The length of rectangle ABCD, the length of this rectangle ABCD is AB times the width. The width of this rectangle ABCD is DA. So in total, we can find out that the area of rectangle ABCD is equal to AB times DA. AB, in total, AB equals to x plus A, and DA equals to x. So AB is x plus A times DA. DA is x. So in total, we should find out that the area of this rectangle ABCD equals to x plus A times x. But we have already found out that according to this equation 2, x plus A times x equals to 12.5. Therefore, we substitute x plus A times x here by 12.5. So in total, we have found out that the area of this rectangle ABCD equals to 12.5 square units. And that is the answer to the question. And again, according to the first method, the area of this rectangle ABCD is equal to 12.5 square units. So we finish with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD according to the second method. First of all, because of the fact that ABCD is rectangle, all those four angles inside rectangle ABCD are right angles. So actually, this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we'll define the center of this semicircle as O, and we will define the radius of this semicircle as x, exactly as we did in the first method. So point O is the center of the semicircle, point A is the point of the semicircle itself, so this is exactly the definition of a radius. Therefore, OA is the radius of this semicircle that is equal to x units in its length according to our definition. We have already found out in the first method that dA equals to x. So I'll not repeat on the same explanation. dA equals to x according to the first method. In the next step, we'll define this point as point N. We'll define line segment OB, this line segment OB as A. And we'll join points M and N together by a straight line. By joining points M and N, we can do peripheral angle AMN. This is peripheral angle AMN. It is very easy to see from the drawing that peripheral angle AMN subtend on AN, that is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees in its size. So I repeat quickly on rule 7. according to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees. In the moment we have a circle, this is peripheral angle ACB. We know that AB is the diameter of this circle, and because of the fact that peripheral angle ACB subtend on AB, that is the diameter of this circle, the size of this peripheral angle ACB that subtend on the diameter of the circle must be equal to 90 degrees. So you can see here that peripheral angle ACB is a right angle. So any peripheral angle that subtend on the diameter of a circle must be equal to 90 degrees in its size. So we can definitely implement rule 7 in our drawing. Why? Because of the fact that peripheral angle ACM subtend on AN, that is the diameter of this semicircle. Therefore, according to rule 7, peripheral angle AMN must be equal to 90 degrees in its size. Okay. The next step we define this angle as alpha, and we focus on this right angle AMN. In this right angle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, we'll focus on this right triangle A and B. This right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, we'll we'll prove that the right triangle A and B is similar to this right triangle A and N. So we'll copy those two right triangles in a new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. We know that the diameter AN is twice as long as the radius of the semicircle. The radius is x, therefore the diameter AN must be equal to 2x. AM equals to 5 units in itself, according to what is given as the question. And side AB of the right triangle A and B is equal in total to x plus a. So actually, those are the two right triangles, A and N, and A and B to the copy from the original drawing. In the next step, we prove that those two right triangles are similar to each other. So write those two right triangles are similar to each other. We prove that. This is angle A, and this angle A is a common angle that belongs to both triangles. It is very easy to see that angle A equals to the right triangle A and B, and the angle A also belongs to the right triangle A and N. So angle A is a common angle that belongs to both triangles. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So actually this is angle MBA, in the right triangle AMB, and it is equal to this angle, that is actually angle AMN, in the right triangle AMN. They are both equal to 90 degrees, and therefore they are equal to each other. As I already mentioned 1 minute ago, this is angle A, here angle A, here also, angle A is a common angle that belongs to both triangles. So we can write down that angle A equals to itself as a common angle that belongs to both triangles. So if we relate to this angle A as it belongs to this right triangle AMN, it will be defined as angle MAN. And angle A equals to itself, so if we relate to angle A as it belongs to the right triangle AMB, it will be defined as angle MAB. So this equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle MAB. This is angle AMB. In the right triangle AMB, and it is equal to this angle. This is actually angle ANM. In the right triangle AMN. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually prove that all the angles of this right triangle AMN are correspondingly equal to all the angles of this right triangle AMB, therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Triangle AMN is similar, this is the sign of similar to the right triangle AMB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM of this right triangle AMB over side AN of this right triangle AMN is equal to side AB of this right triangle AMB over side AM of this right triangle AMN. So repeat again. we will derive the side AM of the right triangle AMB over side NA of the right triangle AMN equals to side AB of the right triangle AMB over side AM of the right triangle AMN. I already showed to you that AM is 5 over AN is 2x, and it is equal to AB. AB is x plus A over AM. AM is 5. So in total, according to equation 1, we actually found out that 5 over 2x equals to x plus A over 5. Here we first multiply this equation, equation 1, and we get that 5 times 5 is 25 equals to 2x times x plus A. Here we divide this equation, equation 1 by 2, and finally get that according to this equation, equation 1, 25 over 2 is 12.5, and it is equal to 2x over 2 is x. So in total this expression equals to x times x plus A. So in total, according to equation 1, we actually found out that x times x plus A equals to 12.5. Our mission is to find out the area of this rectangle, ABCD. Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. Therefore, the area of our rectangle ABCD must be equal to the length of the rectangle ABC times the width of rectangle ABCD. The length of this rectangle ABCD is AB, and the width is dA. So in total, we shall find out that the area that we are looking for in this question, that is the area of rectangle ABCD, is equal to AB times dA. AB is x plus A times dA. dA is x. So in total, the area of rectangle ABCD equals to x plus A times x. But according to equation 1, x plus A times x equals to 12.5. Therefore, we substitute x plus A times x by 12.5. So in total, we found out that the area of rectangle ABCD equals to 12.5 square units. So actually, in both methods, we found out that the area of this rectangle ABCD is equal to 12.5 square units. We finished with the second method. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our mission was to find out the area of this big circle. So in the drawing, we have two circles that touch each other at this point C. Point C is the point of tendency of the two tangents of the two circles with each other. In addition, we have here chord CV, that is equal to 9 units in itself. We have here also chord AC, that is equal to 16 units in itself. And we also have here tangent DE, that is tangent to this small circle at point B. And tangent DE is tangent to this big circle at point M. So if we focus on this common extent point B. From this common extent point B, we have tangent BM to this big circle, tangent BM, and tangent to this big circle at point M. And from the same common extent point B, if we draw this straight line BC and extend it, we get here called AC. So all the requirements of rule 10 are satisfied, and therefore according to rule 10, the following equation is true. That BM squared equals to BC times BA. Again, BM squared equals to BC times BA. So repeat again. If we focus on the common extent point B, according to rule 10, the following equation is true. That BM squared equals to BC times BA. BM is the missing side, so we leave it as it is. And BM squared equals to BC times BA. BC is 9, and BA in total equals to 9 plus 16, that is 25. So BA in total is 25. BA is 25, BC is 9. So in total, BM squared equals to 9 times 25. Here we took a root out of this equation, and we finally found out that BM equals to the square root of 9, that is 3, times the square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. Because again, the length of this tangent BM is 15 units. According to rule 10. In the next step, we did a construction, that is to say, we drew a common tangent at point C. The common tangent that we drew is a tangent that belongs to both circles. The common tangent is tangent to this small circle at point C, and the common tangent is also tangent to this big circle at the same point C. And we define the touching point of the common tangent with tangent DE, this point is point N. So in the next step, we focus on this common extent point N. From this common extent point N, we have two tangents to this small circle, tangent NB and tangent NC. And according to rule 2, they are equal to each other. That is to say, NB equals to NC. In the next step, we join point C and M together by a straight line, and I copy this triangle C and B in a new page, and analyze this right triangle C and B. So actually, this is the right triangle C and B that I copied from the original drawing. According to rule 2, side CN equals to side NB. And we have the rule that states that in front of equal sides in the triangle, there are equal angles. In front of this side CN, we have this angle. In front of this side NB, we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they must be equal to each other according to the rule that I mentioned. So in total, we found out that angle NCB equals to alpha, angle NCB equals to alpha, and angle NBC also equals to alpha. Angle NBC equals to alpha. We continue to focus on this common extent point N. From this common extent point N, we have two tangents to the big circle, tangent NC and tangent NM. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. In the next step, I copied the triangle CMN in a new page, and we analyze this triangle CMN. This is triangle CMN that I copied from the original drawing. According to rule 2, side CN equals to side NM. And according to the rule that I mentioned, that in front of equal sides in the triangle there are equal angles. So in front of this side NM, we have this angle. In front of this side CN, we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal in their sizes, according to the rule that I mentioned. So if the size of this angle is beta, then the size of this angle must be also equal to beta. So in total, we found out that angle MCN equals to beta, and angle CMN also equals to beta. In the next step, I copied the big triangle MCB in a new page, and we analyze the big triangle MCB. This is the triangle MCB that I copied from the original drawing. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees, the sum of the angles in this triangle CMB must be equal to 180 degrees. 180 degrees. So which angles we have in this triangle CMB? We have this angle that is alpha plus this angle that is beta plus this angle that is beta plus alpha. In total, the sum of those angles must be equal to 180 degrees according to the rule that I mentioned. So in this side of the equation we have alpha plus alpha, this is 2 alpha, beta plus beta, this is 2 beta. So in total 2 alpha plus 2 beta equals to 180 degrees. Here we divided this equation by 2 and finally found out that alpha plus beta equals to 180 degrees over 2, that is 90 degrees. So hopefully the big angle MCB is equal to 90 degrees in its side. So it is the right angle. This is the big angle MCB. This big angle MCB is the right angle. It is given us the question that AB is a straight line. If you focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is the right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So if we relate to the big circle, this angle is a peripheral angle. Peripheral ACM is a peripheral angle, and peripheral angle ACM is a right angle. In the next step, we join points A and M together by straight line. By joining points A and M, we create a chord AM. Chord AM is a chord in the big circle, inside the big circle. So we have here peripheral angle ACM, that is a right angle. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. And because of the fact that peripheral angle ACM, that is right angle, subtend on AM, it means that AM must be the diameter of this big circle according to rule 5. So chord AM is the diameter of the big circle according to rule 5. So AM is the diameter of this big circle, and we know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. So the center of this circle must be located on AM, that is the diameter of this circle. So okay, this is the center of this circle, and it is definitely located on AM, that is the diameter of the circle. We define the center of this big circle as O. So point O is the center of this big circle, point M is the point of the circle itself, therefore OM is the radius of this big circle. We define the radius of this big circle as R. And because of the fact that the radius OM, that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever you have a radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I copied the right big triangle A and B in a new page, and we implemented the Pythagoras theorem on this right triangle, triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. AM is the missing side, MB is 15, and the hypotenuse AB is 16 plus 9, that is 25. So this is the right triangle A and B that I copied from the original drawing. This right triangle A and B. AB square, that is the square of the hypotenuse, must be equal to AM square plus MB square. When AB square equals to AM square plus MB square. AB is 25, therefore B square is 25 square, that is 625, and it is equal to AM square. AM is the missing side, so we leave it as it is, plus MB square. MB is 15, therefore MB square is 15 square, that is 225. So in total, we found out that 625 equals to AM square plus 225. If we subtract 225 from this equation, We found out that 625 minus 225 is 400. So 400 equals to AM squared. Here we took out of this equation and finally found out that AM, the missing inside AM, is equal to the square root of 400, that is 20. Okay, the missing inside AM equals to 20 units in itself. But AM is also the diameter of this big circle. Again, called AM is the diameter of the big circle. If the diameter of the big circle equals to 10 to 20 units, it means that the radius must be equal to half of it. So the radius must be equal to 20 over 2, that is 10. Okay, the radius must be equal to the diameter over 2. That is to say, R equals to AM, that is 20 over 2. 20 over 2 is 10. So we found out that the radius of this big circle is equal to 10 units in itself. The radius R equals to 10. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle, of this big circle, must be equal to pi times the radius of the big circle squared. The radius of the big circle is 10, therefore the radius squared is 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. 100 pi is 314.159 square units. So we found out that the area that we are looking for in this question, that is the area of this big circle, equals to either 100 pi square units, so in terms of numbers, the area of this big circle equals to 314.159 square units. So we finish with the first question. In the next step, I presented you the second question, and we solved the second question in two different methods. Our mission in the second question is to find out the area of this rectangle ABCD. So we start with the first method. In the drawing, we have rectangle ABCD, and we have this semicircle. We know that 970 AM equals to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. Because of the fact that ABCD is a rectangle, all those 4 angles inside rectangle ABCD are right angles. In the next step, we define the center of this semicircle as O. We define the radius of this semicircle as X. Point O is the center of the semicircle, point A is the point on the semicircle itself, therefore OA is the radius of this semicircle, that is equal to X units in its length according to our definition. In the next step, we define the point of tendency of DC with this semicircle. This point is point E. And we join points O and D together by straight line. Point O is the center of the semicircle, point E is the point of the semicircle itself, so this is exactly the definition of a radius. Therefore, OE is the radius of this semicircle, that is equal to X units in its length. So, because of the fact that the radius OE, that is equal to X, the radius OE is drawn to point E, that is the point of tendency of tangent DC, with this semicircle. And whenever you have radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. By doing this construction, we created here quadrilateral DEOA. Inside this quadrilateral DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be its rectangle plus a square. So we know to this quadrilateral DEOA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle DEOA, side EO must be equal to the opposite side DA. But EO is X, therefore the opposite side DA must be also equal to X. In the next step, we defined the length of this line segment OB as A, and we defined the length of this line segment MB as B. We joined points O and M together by straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle that is equal to x units in its length according to our definition. In the next step I copied the right triangle OMB in a new page and implemented the Pythagoras theorem on this right triangle OMB. This is the right triangle OMB that I copied from the original drawing. In this right triangle OMB, M all square, that is the square of the hypotenuse, equals to MB square plus B all square. MO is x, therefore MO square is x square, and it is equal to MB square. MB is B, therefore MB square is B square, plus B all square. BO is A, therefore B all square is A square. So in total, according to equation 1, we actually found out that x square equals to B square plus A square. In the next step, I copied the right big triangle A and B in a new page, and implemented the Pythagoras theorem in this right triangle A and B. The hypotenuse AM is 5 according to what is given as the equation, MB is B according to our definition, and side AB is x plus A. In total, AB equals to x plus A. So actually, this is the right triangle A and B that are copied from the original drawing according to the Pythagoras theorem in this big triangle A and B. MA square, that is the square of the hypotenuse, equals to MB square plus BA square. AM is 5, therefore AM square is 5 square, that is 25, and it is equal to BM square. BM is B, therefore BM square is B square, plus BA square. BA is x plus A, therefore BA square is x plus A square. So in total, according to equation 2, we actually found out that 25 equals to B square plus x plus A square. So 25 equals to B square plus x plus A square. X plus A square equals to x square plus A square plus 2 times x times A. In this side of the equation 2, we have B square plus A square. But according to this equation 1, B square plus A square equals to x square. So we can substitute B square plus A square by x square according to equation 1. We actually did it and found out that (25) equals to B square plus A square is x square, and we have x square again, plus 2xa. So 25 equals to x square plus x square is 2x square plus 2xa. We divided this equation 2 by 2, and finally found out that 25 over 2 is 12.5, and it is equals to 2x square over 2 is x square, and 2xa over 2 is xa. So according to equation 2, 12.5 equals to x square plus xa. So 12.5 equals to, here we took out x as a common factor from those two expressions. So what is left from x squared after we took from it x as a common factor? What is left is actually x. And what is left from xa after we took from it x as a common factor? What is left is it is actually a. So in total, according to equation 2, we actually found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width of the rectangle ABCD. The length of this rectangle ABCD is AB, and the width is DA. So in total, the area of rectangle ABCD must be equal to AB times DA. AB is x plus A, and DA is x. Repeat again. AB is x plus A, and DA is x. So in total, the area of rectangle ABCD must be equal to x plus A times x. But according to equation 1, x plus A times x is 12.5. Therefore, we can substitute x plus A times x by 12.5. And finally found out that we are looking for this question, that is the area of rectangle ABCD equals to 12.5 square units according to the first method. We finish with the first method. In the next step I present it to you how to find out the area of this rectangle ABCD according to the second method. So first of all, we know that all the angles inside rectangle ABCD are right angles. So those four angles are all right angles. We define the center of this semicircle as O, and we define the radius of this semicircle as x, exactly as we did in the first method. Point O is the center of the semicircle, point A is a point on the semicircle itself, therefore line segment OA is the radius of this semicircle that is equal to x units in itself according to our definition. We already found out in the first method that dA equals to x, so I'll not repeat on the same explanation. dA equals to x units in itself according to the first method. In the next step we defined line segment OB as A. We define this point as N. In the next step we join points M and N together by a straight line. By joining points M and N we get a deal peripheral angle AMN. And because of the fact that peripheral angle AMN subtend on AN, that is the diameter of the semicircle, peripheral angle AMN must be equal to 90 degrees in its size according to rule 7. Here, peripheral angle AMN equals to 90 degrees in its size according to rule 7. In the next step, we define this angle as alpha. So in the right angle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third piece angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in the triangle. Likewise, we focus on the right angle A and B. Now, on the right angle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third piece angle must be equal to 90 degrees minus alpha. AB in total equals to x plus A. AM equals to 5 units in itself, according to what is given as the question. And AN, the diameter AN of the semicircle, equals to 2x. It is twice as long as the radius that is x. So in the next step, we copy the right angle A and B and the right angle AMN in the page, and we prove that those two right angles are similar to each other according to angle similar to rule. But before that, this is angle A. Angle A belongs to the right angle A and B, and angle A also belongs to the right angle AMN. Therefore, angle A is a common angle that belongs to both angles. Actually, those are the two right angles AMN and AMB that are coming from the original drawing. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, as I already mentioned 1 minute ago, this is angle A, that is a common angle that belongs to both triangles. So we can find out that angle A equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the triangles of this right angle AMN are correspondingly equal to the triangles of this right angle AMB, and therefore those two right angles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM of this right angle AM, derive the side AM of this right angle AMB over side AN of this right angle AMN equals to side AB of the right angle AMB over side AM of this right angle AMN. And again, we will derive that side AM of the right angle AMB over side AN of the right angle AMN equals to side AB of the right angle AMB over side AN of the right angle AMN. AM is 5, AN is 2x, AB is x plus A, and AM is 5. So of course multiply this equation and found out that 5 times 5 is 25, so 25 equals to 2x times x plus A. Here we divided this equation 1 by 2, and finally found out that 25 over 2 is 12.5, 2x over 2 is x. So in total this expression equals to x times x plus A. So according to equation 1, we will find out that 12.5 equals to x times x plus A. Our mission is to find out the area of this rectangle ABCD. Okay. We have to find out the area of rectangle ABCD. So what is the area of rectangle ABCD? Actually, you know that the area of any rectangle equals to the length of the rectangle times the width. And therefore the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width of rectangle ABCD. the length of the rectangle ABCD is AB, and the width is DA. So in total, again, the length is AB and the width is DA. So in total, the length of the rectangle ABCD must be equal to AB times DA. AB in total is x plus A, DA is x. And again, AB is x plus A and DA is x. So in total, the area of rectangle ABCD must be equal to x plus A times x. But x plus A times x is 12.5. So we substitute x plus A times x by 12.5. And we found out that the area of rectangle ABCD is equal to 12.5 square units. So in both methods, we found out that the area that we are looking for this question, that is the area of this rectangle ABCD, is equal to 12.5 square units. Okay, thank you very much.